Mike. Hi, everyone. So I gave a seminar here in 2015, and I thought that I'd better tell you something completely new that I hadn't worked on in 2015. So if any of you were here in 2015, don't worry, I'm not going to give the same talk. Thanks very much for the invitation. Very nice to be here. So I'm going to talk about some work that I want to emphasize the contribution of the people who've been working with me here. So there's a couple of PDRAs, Christina Schottler, who's now at Imperial, Joe Eaton, who's at Sheffield, and then a couple of PhD students who George Blaylock-Squibbs recently finished, Rana Nicholson did a PhD with me a few years ago. And then I also want to highlight the contribution of some undergraduate and postgraduate master students, Mickey Patel, Cheyenne Bullius, Mark Smith, and Lewis Woods, all worked with me on projects in Sheffield. So what I'm going to talk to you about is the origin of short-lived radioactive isotopes in our solar system, and give you an idea of what the debate is about their origin and why we're still quite confused about how they got into our solar system and what they do once they're in our solar system. So what are they? Well, we think there are, in the oldest objects in the solar system, so-called chondritic meteorites. This is a bit of a chondritic meteorite. They have these things called calcium aluminium-rich inclusions. And those inclusions in the minerals have the decay products of short-lived radioactive isotopes. So we've got aluminium-26, that has a half-life of only 0.72 million years, so quite short on an astronomical timescale. And then we have iron-60. So iron-60 has a slightly longer half-life, 2.5 million years. And why this is interesting is that aluminium-26, when compared to the stable version of aluminium-27, and then iron-60 to iron-56, they're much more abundant in our solar system than they are if you just look at the interstellar medium. So we think there is an overabundance in our solar system, and because they're in the oldest objects that we know about in the solar system, those short-lived radioactive isotopes were either put into our solar system very, very early on, or the solar system formed from material that was already enriched in these isotopes. And then there's quite a bit more aluminium-26 compared to iron-60, so that ratio is about 8. And what do these isotopes do once they're in our solar system? This is the amount of radiogenic power. So think of this as the heat that's coming from these short-lived radioactive isotopes over time in the early solar system. And you can see that we've got some radioactive isotopes, such as uranium-238, thorium-232, that are still producing heat in our planet today. But you can see that the contribution from aluminium-26 and iron-60 dominates the early radiogenic heating in our solar system. And so what does this mean if you're thinking about a planet? So this is something I stole from Tim Lichtenberg's Protostars and Planets 7 review article. So this is a schematic of what the effective heating from short-lived radioactive isotopes is. And if you go from left to right, this is progressively more heating. So this is what happens to the volatiles. So eventually you start losing very high volatile elements, and the rock dries out and continues to dry out. And then eventually, if you have enough heating, you start losing moderately volatile elements as well. The middle panel shows what happens to metals. So if you have metal suspended in your planet, then you get what we call differentiation. So the metals sink to the core of the planet, and eventually you get a fully metal core. So again, this is with successively more and more heating from these isotopes. And then if you're just talking about the rock, the sort of silicates in our planet, then you have a solid silicate mantle with when you don't have any heating, then eventually you get convection happening in the rock and partial melting. And then finally, if you have enough heating, you get what's known as a magma ocean. So this is essentially where the planet is, or the rock element of the planet is completely molten. So you can see that if you have enough of this short-lived radioactive isotopes, you get significant heating in the planet, and that changes the composition of the planet, or the kind of phase of the planet. This is what happens to the water content in the rock. So this is taken from another of Tim Lichtenberg's papers. So what Tim's showing here is the bulk water content in a rock. So We get more and more water over here to the right. And then this is the planet mass. And so what this is that we're adding together planetesimals. We're forming more and more massive planet-like objects. And the color scale is basically showing how much aluminium-26, so one of these short-lived radioactive isotopes, how much of this aluminium-26 was included in that planetesimal. So the red is 10 times the amount that was in the solar system to begin with. And the gray points, that's similar amount of aluminium-26 to the solar system. And the blue points are where there's no aluminium-26 in these planetesimals. And so you can see the things which have 10 times the amount of aluminium-26 as in the solar system have very little water. So what's happening is these planets are being pushed, the planetesimals are colliding, being pushed together, they're forming more massive things, and these objects are desiccating. They're losing their water content as they're forming higher and higher mass objects. Why is this important? Well, we think that the heating from these short-lived radioactive isotopes is enough to sustain plate tectonics on our planet. So when we think of plate tectonics, we often think of this as a very negative thing. So they cause tsunami, earthquake, volcanoes, and these natural disasters, disproportionately affect the poorest people on the planet. But we think that plate tectonics are essential for sustaining a breathable atmosphere on the planet as well. And some people have even gone so far as to say that you only have advanced civilizations if you have heating from aluminium-26, because this gives you the conditions conducive to advanced life forming on planets. It's a somewhat controversial opinion, but it is in the literature. So what you would expect is if you had no heating from these short-lived radioactive isotopes, then the planet becomes progressively more volatile rich, and you have what geophysicists confusingly call an ocean planet. This is actually a very ice-rich planet where the ices have mixed with the silicates in the planet, okay? And so you have a silicate mantle and then a high-pressure ice layer here. And then what geophysicists call shoreline planets are planets like ours. So these are planets that have a very thin crust and a liquid water ocean on them. And so the idea is if you have no aluminium-26, you end up with these ice-rich planets. If you have aluminium-26 at levels similar to that in our solar system, you have these shoreline planets. You'll notice that there's a prediction that the radii of these planets should be different. So if, and it's a big if you manage to observe two terrestrial planets with the same mass, same size, same composition, but one of them had heating from aluminium-26, then you expect a difference in the radius that might be observable with Plato. Okay, so this is a deviation from radius with no aluminium-26 compared to solar system levels, and then 10 times solar system levels. And so the prediction is that Plato is going to be able to observe such small differences in the planet. Just to remind us what Plato is. Basically Kepler on acid or on speed. So basically the next generation planetary transit kind of thing. Now, interestingly, and I do feel for Joe Eatson, who was working on this for the best part of the last year, there's not really any difference whether or not you have iron-60, heating from iron-60 or not. So the aluminium-26 completely dominates the early heating. And what Joe did was he basically ran some models similar to these ones, but included, these models don't include iron-60, these models do. And so this is showing the retained water fraction, so how much water is left over compared to what you put into the simulation. And this is the planetesimal radius. And what Joe found was that you need 1,000 times or even 10,000 times the amount of iron-60 that we know was in the early solar system in order to make a difference to the heat evolution of the planetesimals. So it's important that we explain where the iron-60 came from in our solar system, but it does very little in a geophysical context to the evolution of our planet. So where does the aluminium-26 come from, or where does the iron-60 come from? There's several ideas. So the first is that they're produced in cosmic rays or via cosmic ray spallation. So this is non-thermal nuclear synthesis. and produces boron, beryllium, and lithium-4 in the interstellar medium, can produce aluminium-26 and some other short-lived radioactive isotopes in our solar system. But these come from essentially from flares from our sun. And so you wouldn't expect aluminium-26 to be distributed homogeneously in the solar system, which we think it is. And you would expect the same abundance of aluminium-26 as other elements created via, which we know are created via cosmic ray spallation. And that's not observed. And crucially, it doesn't produce iron-60. So even if cosmic ray spallation is responsible for some of the aluminium-26, we need a different method or different avenue to produce iron-60. So let's tie this back to star formation and nearby astrophysics. Where do we get the aluminium-26 and iron-60 from? Well, where are most stars born? So a lot of star forming regions that look like Chameleon-1. So these are low mass star forming regions, contain a few hundred stars. They don't contain any very massive stars, but you don't have to go very far to find something like this. This is the Orion Nebula Cluster. This is the closest star forming region to the sun that contains O-type stars. And there's 4 very bright stars in the center. These themselves might be multiple systems. There might be 7 or 8 bright stars in the center. And so a big question, and I would say it's an open question, people like Mike kind of do a lot of work to try and answer this, is do most stars form in these regions where they're kind of very massive, rich regions where there's lots of massive stars, or do most stars form in these low mass regions? And we don't really know the answer to that yet. In terms of initial mass function, if you want to produce one massive star that's going to produce aluminium-26 and iron-60, then you're looking at probably 300 or so low mass stars at least. And if you want to produce several massive stars, then you're going to be talking about a distribution of stellar masses with hundreds of low mass stars. So the point is that if you have a very massive star that can produce aluminium-26 and iron-60, then you're going to have lots of low mass stars, a lot of them less massive than the sun, but a lot of them are similar mass to the sun. And so if the sun was born in something like the Orion Nebula Cluster, then potentially you can envisage lots of enrichment occurring in these star forming regions. Also, lots of young stars, pretty much nearly all young stars, have a circumstellar disk. And these are sometimes called accretion disks, or sometimes called protoplanetary disks, the same type of object. And before ALMA and all the rest of it, these disks were found via looking at the black body spectrum of a star. So stars generally have a very good black body spectrum. And lots of young stars appear to have an infrared excess, so an excess of flux at infrared wavelengths. And the interpretation of this is that this is due to micron-sized dust particles in a disk around the star, absorbing radiation from the star and then re-emitting at long wavelengths. And this is now more than 20 years old. So this was the first plot that kind of showed the fraction of stars with an infrared excess as a function of the age. So what this is, each data point here is an individual star forming region. And this is looking at the infrared excess as a function of the age of the star forming region. So you can see that lots of young star forming regions, lots of stars have this infrared excess. In slightly older regions, very few have. And this has been completely superseded, but the general result still holds by things like ALMA and also other kind of infrared surveys as well. So this is a gallery of disks, protoplanetary disks around young stars. You can see that no two disks look the same, which I like. This is the thing I like most about this work. And also, people have repeated the work that Heisch did back in 2001. And this is a more recent paper from Richard et al. And you can see that we're no longer calling this an infrared excess because we're convinced that it's a protoplanetary disk. And you can see that, again, very young things that are about 1 million years old all have disks. And things that are only kind of 4 to 5 million years old don't have disks at all. Now, calculating ages of young stars is notoriously difficult. There's an uncertainty on this, but the point is that within about 10 million years, no stars have these very kind of sort of fine dust grained homogeneous disks. We think that they're already forming planets. We think that these kind of dark lanes in these disks are the effects of a giant planet that's already formed, that's carving out an orbit around the disk. So lots of stars have planets, lots of stars are forming planets, and this happens really quickly. So one idea for getting aluminium-26 and iron-60 into the solar system is that the sun, with its protoplanetary disk, just so happened to be near a massive star that exploded as a supernova very, very early on when it was still forming planets. And the reason that this works, or in theory works, is that you have a young star-forming region, there's lots of low-mass stars, there's a couple of massive stars. This would give a roughly homogeneous distribution of aluminium-26 and iron-60. And so what we decided to do was model this in quite a crude fashion, actually. So we run n-body simulations of a star-forming region, okay, we say that the stars have formed, and we track where the massive stars are compared to low-mass stars. And when the massive stars explode supernova, according to the stellar evolution model, we then say, okay, how many low-mass stars are within a certain distance of the massive stars that explode as supernova? So this is before the simulation starts. This is just looking at a rotation of the star-forming region. The red points are massive stars. So this star-forming region contains about 1,500 stars, and there's at least 10 of them that are more massive than about 10 solar masses. Very rapidly, you wipe out all of the initial structure and the filamentary nature of the star-forming region. This is just through dynamical encounters with other stars. And then you can see that eventually, most of the massive stars end up in the central regions. This is a phenomenon called dynamical mass segregation. So what we do is then we just look at where the low mass stars are in relation to the high mass stars when the high mass stars explode as supernovae. So this is a cumulative distribution. Each colored line here is a different star-forming region. So we repeated this simulation 20 times to get an idea of the statistical variance. And the colored lines represent the distance of stars like the sun. So between 0.8 and 1.2 solar masses, the distance of these stars from the supernovae. First thing you'll notice is in a couple of these star regions, the massive stars are ejected before they explode as supernovae. So if you read a textbook on three-body dynamics, it will tell you that massive stars kick out low mass stuff. Well, not always, because if you have intermediate mass stuff forming a binary, the binary bullies out the bully. The bully gets bullied almost. So you can eject the most massive stars. So we're not getting enrichment in these star-forming regions. And even when you do get enrichment, often you're too far away to have any significant amount of enrichment. So this was some work that we did about 10 years ago, where we estimated that the amount of enrichment that the solar system would experience is actually quite close. You need a very close encounter with a supernova, so between 0.3 and 0.1 and 0.3 parsecs. So there's a couple of, I would say, caveats, problems, issues with this idea. First of all, the sun has to be in the right place at the right time. So most sun-like stars are too far away. It's actually quite difficult, we think, to couple the hot ejector that you get from a supernova explosion to what is essentially a cold protoplanetary disk. So some people have tried modeling this, and what happens is the ejector just passes through cold disk. So it's quite difficult to couple the ejector together whilst it's still hot. And then also, if you look at the orbits of the massive stars, of the low mass stars with respect to the massive stars, so this is the orbit of low mass stars around the cluster center, and each colored line here is an individual star, and you can see that you just literally are in the right place at the right time. When the supernova explosion goes off, shown by this dotted line here, then you're in the right place at the right time. Before then, you might have been experiencing lots and lots of dynamical encounters with other stars, because these stars are passing through the center of the star-forming region every half a mega year or so. And so when they're doing that, they're going to have interactions with all the other low mass stars. And so this could be quite chaotic or catastrophic for our young solar system. Also, the aluminium-26 to iron-60 ratio is too low. Okay, you get far too much iron-60 from these supernovae explosions. Tim Lichtenberg did this much more kind of comprehensively a few years later. And so what Tim has done here is repeated a lot of these simulations and then worked out the amount of radiogenic heating. So this is the heat coming from short-lived radioactive isotopes once they're in a planetary system. And this vertical dotted line is the value that has been calculated for the early solar system. And so Tim varied the initial conditions of the star-forming region. And what he found was that there's a huge spread in the amount of heating that you'd expect. So in these star-forming regions here, you're getting virtually no aluminium-26 and iron-60 into the system. In these star-forming regions here, you're getting a lot more than is in the solar system. Now, we've extended this work further to look at not just the contribution from the supernovae, but the winds from the massive stars before they explode supernovae produce a lot of aluminium-26 as well. Okay, so what we're doing here is now looking at the cumulative distribution. Again, each of these colored lines is an individual simulated star-forming region. We're looking at the cumulative distribution of the 26 aluminium to 27 aluminium ratio. The dotted line is the value measured in the solar system. And so this plot here is showing simulations where we just have supernova explosions. And you can see that most of the stars in these simulations are not commensurate with the measured value in the solar system. However, once you start introducing enrichment from the winds of the massive stars, so before the massive stars explode as supernovae, then you get a very different distribution. So we've took two approaches here. First of all, we assumed that the winds from these massive stars are entrained in fairly local bubbles around the massive stars. So what that means is there's more material for a low mass star and its disk to pass through, but some low mass stars and their disks will never pass through that material. On the right-hand side here, we've got the supernova, and then we've assumed that the winds are dispersed quite rapidly. So the winds are dispersed throughout the rest of the star-forming region. And you can see that, you know, these, the colors, and apologies if the colors don't come out on the projector very well, but we focus on this orange line here. You can see that there's much more enrichment in this star-forming region when we assume the stellar winds are important. And then, if we assume that stellar winds are important but are dispersed over the star-forming region, you can see that pretty much every star in this simulation has an aluminium-26 ratio that's higher than that in the solar system. And you can see that this varies by, what's that, 4 or 5 orders of magnitude. So this is hugely stochastic. These simulations have identical initial conditions. So all you're seeing here is a difference due to the initial mass function, which is random but consistent with the field, and then the dynamics of the individual star-forming. This is the effects from iron-60. Sorry, this is the ratio for iron-60, these star-forming regions. Now, this is where we start to encounter problems with this idea, big problems, in my opinion. This is supernova. So you only get iron-60 from supernovae. And after 5 million years, when the sun's protoplanetary disk might still be forming planets, only 3 star-forming regions have a massive star that is exposed as supernova. Once you get to 10 million years, you have most star-forming regions have a massive star that exposes supernova. And the dot dash and the dashed lines are different measurements for the amount of iron-60 in the solar system. So I want to point this out, that this is quite a controversial measurement. There's not really agreement on this, but you can see that we need to wait until about 10 million years in order to get any sort of amount of iron-60 into a planetary system. And after 10 million years, you've probably already formed the planetary system. So the distribution is not going to be homogeneous, which is what we observe in the solar system. This is unfortunate because it matches the ratio of aluminium-26 to iron-60 really nicely. So the ratio of this in our solar system is about 8. So you can see the supernova only doesn't really work. But once you start adding local winds, you can see that in this area here, we're matching the observation in the solar system. And then with these dispersed winds, we're also matching it quite nicely for a quite significant number of stars. So the issue, unfortunately, is that the stellar evolution models we were using were slightly out of date, and they've been superseded by a new set of models. And if I can summarize these new models, basically nothing over 25 solar masses explodes as a supernova, collapses directly to a black hole. And furthermore, we think that massive stars rotate. If a massive star is rotating, it essentially rejuvenates itself and it delays exploding as a supernova. So in the models I've just shown you previously, we were getting supernova explosions after 4 or 5 million years. That doesn't happen in these updated stellar evolution models. Okay. This graph is essentially showing that. So let's see, if I just focus on the iron 60, so the previous models were producing iron 60, a little bit of iron 60 here, and then supernovae of stars that are more massive than 25 solar masses, producing a lot of iron 60. You see that by the black dashed line here. And these kind of red colored lines here show you what the latest models are now predicting. Of course, stellar evolution models are subject to lots of uncertainties as well, but the field tends to be really is kind of shifting towards this new idea that things more massive than 25 solar masses just don't produce any ejecta at all. So based on this, we repeated our calculations with these new stellar evolution models, and you can see that previously, where we had quite a lot of iron 60 after 10 million years, we've got virtually no iron 60 after 10 million years. That's before we've even started worrying about the timescales for planet formation. There's another problem with this idea as well. I thought, by the way, I'm trashing my own ideas before I get on to trashing other people's ideas. I think it's only fair you do it that way around. The massive stars that produce enrichment via supernovae also produce very intense photoionizing radiation. That photoionizing radiation is strong enough to evaporate the gas from protoplanetary disks. Not the protoplanetary disk as a whole, but the gas from a protoplanetary disk. So these are some models that are done by Tom Howarth's group down in Queen Mary in London. So what Tom is showing for different FUV radiation strengths. So this is, the red line is 10 times the background interstellar medium radiation flux, and the dashed line is 10,000 times the interstellar medium radiation flux. And so the solid lines are the dust content in a protoplanetary disk. So you get rid of a little bit of the dust, but then it remains pretty constant. But the dashed lines here are the gas content in the protoplanetary disk. And basically, if your radiation field strengths are strong enough, you completely evaporate the gas from a protoplanetary disk on very, very short timescales. These are some models in which we followed the evolution of the fraction of disks that have gas over time. So the color lines here are individual simulations where we're calculating the fraction of stars that have a disk and over time. And this is a very high density star region. This is a sort of moderately average density star region. And this is a low density star region. The data points here are the data from this Richard paper I described a few slides back, where we're looking at the fraction of protoplanetary disks that are observed. And what you see here is that the fraction of disks that contain gas drops quite significantly due to this very high radiation field in the Starfall region. And the more physics, the more realistic physics you add to these disk models, the worse the problem becomes. So let me just, if you focus on the middle panel. So that's what happens if you just let the disk kind of sit there and you're bombarding it with radiation. Disks are fluid entities, so they expand due to viscous evolution. And when you allow the disk to expand due to viscous evolution, that makes the disk larger, makes the density of the edge of the disk lower, and you evaporate even more and more material. So if I flick between the two panels, you can see that we basically destroy all of the disks or all of the gas in the disk before you've really got any chance of enriching the protoplanetary disk with the shortened radioactive isotopes. This is a problem because in our solar system, we have two gas giant planets, Jupiter and Saturn. And in order to form those planets, you need quite a lot of gas hanging around. Okay, so this is simulations where we're showing the amount of gas in the disk. So horizontal dotted line is Jupiter's mass against the aluminium-26 to aluminium-27 ratio. And the vertical dotted line is the solar system enrichment levels. So in our simulations, we really struggle to produce the amount of enrichment that we observe in the solar system, but retain enough of the disk that we would be able to form Jupiter and Saturn. So blue points are after 4 million years, black points are after 10 million years. So in order to do this, we want to do this quickly before the planets have had a chance to really kind of form. And so if you look at the blue points, we see very few systems that are able to retain enough gas to form Jupiter and Saturn, but are enriched in the right amount of aluminium-26. And this is a similar argument, but just for the gas radius of the disk. So we think Jupiter and Saturn probably formed at a few AU, and basically there aren't any disks that are larger than about 1 AU once we've obliterated them with all of this FUV radiation. It's even worse for iron-60 because iron-60 doesn't get delivered to the solar system until much later on. And by that point, you've already got rid of pretty much all of the disks or all of the gas in the disk. And so you don't get anywhere near to producing the solar system levels of iron-60, and you don't retain enough of the gas to form Jupiter and Saturn. Those plots I just showed then, that's the best case scenario. That's assuming the old stellar evolution models when things explode much earlier on. These are the new stellar evolution models. You can see that we're an order of magnitude away from getting anywhere near the observed values. So this is what we call the direct pollution argument for the solar system. And for forming our solar system, it doesn't seem to work. So what are the alternatives? Some people think that the solar system was already pre-enriched in aluminium-26 and iron-60. How does this work? Well, this borrows a fairly old idea in star formation, which is that one star formation region, when the massive stars explode supernovae, can then trigger a new burst of star formation region in the giant galactic cloud, which can then trigger another burst of star formation. So this model proposes that you form some stars in giant galactic cloud. Some of them will be massive enough to explode as supernovae. They propagate a shock wave through the cloud, and that shock wave contains iron-60. This then forms a new generation of stars. One of those stars will be massive enough that it evolves as a Wolf-Rayet star. So this is a star more than 20 solar masses. And that Wolf-Rayet star produces a wind that is rich in aluminium-26. And that then induces a third generation of star formation in this ring here, one of which is our sun. Okay. So by construction, this gives the right amount of aluminium-26 to iron-60. I personally am not a fan of this for a couple of reasons. First of all, we have the same problem with the stellar evolution models. Okay. We're not getting any sort of supernova explosion until after 10 million years. So what that means is that if you observe what looks like sequential star formation, so a star formation here, a younger one here, and a younger one here, the age gap between those star formation regions is going to be very high. It's going to be order 10 million years between each one. And so this is showing how much iron-60 there is over time, and show how it decays over time. So you can see that we're plotting, after the first supernovae that are exploding after a few million years, you maintain a fairly constant amount of iron-60. But if you adopt the new stellar evolution models, you can see that we're waiting until after sort of 7 to 10 million years before producing enough iron-60 that would explain the solar system. As a dynamicist, if you put one star formation region here that star forming region is not going to sit and do nothing. That star forming region is going to try and relax. Star forming regions relax by expansion. And so if you form one star forming region after and form another one, you trigger another one after a certain amount of time, the first star forming region is going to expand. And so the second star forming region is also going to expand. And so after about 10 million years, you'll get age dichotomies in the star forming region. So if you're just looking down the line of sight at star forming region, you're going to see one star forming region that appears to be, well, you're going to see a population of stars that are 10 million years old, and you're going to see a population of stars that are 20 million years old, and they're going to be blended together. Now, there is a bit of controversy about age spreads in star forming regions, but certainly none that are 20 million years in size. So I think that this is a bit of a problem for this pre-enrichment scenario. Mike, how long have we got left? 10 minutes or so? Or do you want to?
Yeah, like 5 minutes.
Five? Okay, we can go through this in 5. So this is my current favorite idea, just to put all my biases out there on the table. This is my favorite idea for getting aluminum 26 and 960 in the solar system. You get it from asymptotic giant branch stars. So an asymptotic giant branch star, if you don't know, is a point in the stellar evolution of an intermediate mass star. So something that's between 1 and 7 solar masses. And these stars dredge up an incredibly large amount of material as they're going through this AGB phase. And they have very strong winds. So they can produce about 10 to the minus 4 solar masses per year in their winds. And they produce a lot of iron 60 and aluminum 26. However, you don't expect AGB stars to be anywhere near young star forming regions that have stars that are forming planets. But Gaia is able to trace back stars to their birth star forming regions. Okay, so this is a color magnitude diagram showing runaway stars. So these are stars that have been ejected from a star forming region and where we've been able to trace them back to their birth star forming region, essentially by drawing lines back to the birth star forming region. So you have runaway stars, and then you have a lot more walkaway stars. So these are moving at much slower velocities. This is an animation. So this is a star that's ejected from one star forming region, Arc's impression. It's got a protoplanetary disk, and all of a sudden, it then encounters a new star forming region. So the idea behind this is that a planetary system might be influenced by both the star forming region that it was born in and a star forming region that it might encounter. And the same is true for a much older star. So you can form an older star somewhere, it kind of wanders around the galaxy, and our idea is that it encounters a young star forming region and enriches the protoplanetary systems in the young star forming region. So I'll just skip this. So this is where we were looking at runaway and walkway stars in NGC 2264. This is a completely serendipitous discovery. So we were looking at this to try and constrain the initial density of this star forming region. The number of runaways and walkway stars tells you about the initial density. And then we found that thing up there on the giant branch, and it traces back to this star forming region at the same time that these stars were forming. We think it's an AGB star. So our idea for the solar system enrichment is that the sun formed in the star forming region, and an AGB star just came wandering through and enriched it in aluminum 26 and iron 60. This is what you'd expect. So this is from a simulation very similar to the one I showed earlier, where we're just letting the stars interact with each other. This is the amount of aluminum 26 in the solar system, horizontal dash line. And then this is the amount of iron 60 in the solar system. And if the AGB star is relatively massive to begin with, if it's about 6 or 7 solar masses, the amount of aluminum 60 and iron 60 you'd expect, aluminum 26 and iron 60 you'd expect, intersects the observed ratios in the solar system. So that was a lovely Friday afternoon when that graph just appeared on my computer screen. It's one of those things that we did not plan this at all. This is completely fortuitous, this discovery. And if you calculate the amount of heating from radioactive isotopes, based on this stuff here, that ratio there, if you calculate the amount of heating, you get at different times. So these short-lived radioactive isotopes decay, but you get heating that's commensurate with the value calculated for the early solar system. So I've told you about short-lived radioactive isotopes in our solar system. I've told you about the kind of uncertainty about how they got there, how much of them there is. There's much higher amounts of iron-26 and probably iron-60 than there is in the interstellar medium. So that's the important point. And also, the other important point is that aluminum-26 vastly changes the internal evolution of a planet compared to if you don't have any at all. They're produced by massive stars, but no model satisfactorily explains their inclusion in the solar system because it tends to affect other assumptions about how our planetary system formed and evolved. And in case you weren't convinced about my bias, here's my bias again. This is an artist's impression of an AGB star wandering through a young startle region. Thank you very much.
Thank you, Richard. So we have plenty of time for questions. Perfect.
Thanks for this very nice talk. I'm sure you know the paper by Fujimoto et al., where they do the interstellar medium of a larger part of the galaxy, and have in their gas dynamical code have the an embodied part and follow star and planet formation. And if I'm not mistaken, they find that just putting in winds and supernova into the simulation, they find lots of planets that follow their simulations that have kind of the right ratio.
Yeah.
So could you comment on that?
Yeah, so this goes back to basically this problem here. The photo of the same massive stars that are doing the enriching are also photoevaporating the gas component of the disk. So if we want to explain our solar system that has two gas-rich planets, then I don't think you can retain enough gas in the protoplanetary disk, even if you get the right amount of enrichment. Now, what that's not precluding is massive stars and their winds enriching other planetary systems. So for instance, if you were to observe a planetary system that didn't have any gas giant planets, and you could observe heating from aluminum-26, then that might well have been produced from the massive stars. My argument here is that once you introduce the massive stars into the equation, you also have to account for the photoevaporation, which can destroy the gas in a protoplanetary disk.
Thanks.
Martin.
So maybe I'm being naive here, but your preferred model involves us getting quite lucky, or
Yes,
proto Earth getting quite lucky. The chances of this flyby at exactly the right type of star must be very low. So,
Yeah.
you know, now that's fine because anthropic principle and all that kind of thing. But you would then make some predictions about distributions of elements in other solar systems. Any chance that could be followed up?
Yeah, so it's basically my next project is to actually calculate how likely it is that we would have a close encounter with an AGB star. So the work I cited from 30 odd years ago was basically looking at where AGB stars are in relation to the sun today, and that doesn't really tell you what was happening at the formation point. So yes, I agree. I mean, I said it's my favorite interpretation of how we got SLRs into the solar system. I'm not convinced it's kind of it's certainly very rare. I just think it's more likely than the other scenarios on the table.
I mean, there's a sense in which if you have to invoke a whole bunch of rare things to make the Earth happen, it explains a bunch of things like not being visited by glowing sources quite as often.
Yeah.
So you get some numbers down that want to be down, but you can't have it so rare that it's.
So actually, I think that there's a potential thing with these models here. So I've said that pollution from winds and supernovae isn't going to explain SLRs in the solar system because of the photoevaporation of the disk. But if you could somehow shield the protoplanetary disk of the sun from some of that FUV radiation, potentially just from leftover gas and dust from star formation, that's not really taken into account in the models. So that would be a caveat. Yeah.
I've got a question.
Yeah.
So when you're talking about these polluters, how local do they have to be to the forming sun? Because there are definitely some, maybe not individual star forming regions, but star forming complexes that do have like 20 million year age spreads, like the SCOSEN association has large
Yeah.
different segments that have different ages.
So you'd have to be within about a parsec, half a parsec. The photoevaporation, interesting, photoevaporation operates on kind of larger distance scales. So for something like SCOSEN, SCOSEN doesn't really have lots of O stars, but SALOB2, for instance, it's a low density region, but there's so many O stars that the FUV field, the G naught field, will be really high. But yeah, certainly SCOSEN, you're talking about kind of a distance of about half a parsec.
Okay. And so having more high mass stars would help this because it would also just up the total UV field.
Yeah.
Other questions?
Pretty much that dust shielding, surely we know, roughly speaking, how much dust shielding there could be, because we've got information about the SEGs of the protostars from outside. That tells us they're not all acidly dusted fairly.
Yeah. I mean, I think the problem as well is you get kind of very variable extinction in star regions. So even in one star region, some areas of the region there's no just extinction. Other regions there is, and also everything's dynamic. So the stars move around. They're not
carrying around this.
Exactly.
One more from me. So I guess on the same topic of dynamics, how much do these depend on assumptions about the dynamics? Like, does it, if things, a lot of your clusters look like they kind of hold together rather than just kind of immediately dispersing?
Yeah.
And does that affect things?
So this is the kind of, I would say this is you can, so actually Joe, my postdoc, is working on something at the minute. He's kind of going to look at how this varies as a function of star density. So we kind of had so many variables in these models that we kind of kept the star density constant.
Yeah.
But the fact that we got this much stochasticity in what essentially is the same simulation made me certainly kind of reluctant to kind of add any more information to the paper. But we are working on it. I would say density matters, but only if you go to really low densities. You go really low densities, you don't get any enrichment, and then the FUV field is very, very low. But once you get up to densities of few tens to 100 solar mass per cubic parsec, you kind of saturate out the amount of FUV radiation. So you have the same problem no matter what the density is. And there, the higher the density, the more enrichment you get. But also the higher the density, the more dynamic encounters you get with other stars, which can do other things to the planetary system that you certainly might not want to do with the solar system.
Thanks. I'll check online. No online questions. Any other questions? Yeah.
There's still time. So this makes me connect to the observations I was involved in, the gamma ray observations in the galaxy of aluminum 26, which showed quite large Doppler shifts, which we interpreted in a way that aluminum 26 can actually stream in large superbubbles, so has some time where it can actually cross distances, and that's why we're seeing such hundreds of kilometers Doppler shifts. And so I was wondering if that solves perhaps the shielding problem, so that if the massive star ejector, you can take them, they travel maybe 100 parsec to the next star forming region, and then mix there. Is that something that could be viable?
I don't know. It's well out of my area of expertise. Not that I have one, but no. I don't know. It's interesting point there.
There's dilution. You can get that. If you have a source right next to your protoplanetary disk, you can get the right amount of stuff. If you've got these giant winds blowing around, they're surely going to be very low density.
Yeah. Yeah, you probably need the right distance and so on. I agree. Yeah.
Something like correlating speed.